Okay, let's start with this. So I do have recorded answer keys for the practice finals in Blackboard. The problem with them, and I actually loved recording this way. I still have it, but I have what was called a smart pen, or is called a smart pen. And the pen had a camera in it and a microphone. So you could write on special paper that they supplied, and the pen knew where it was on the page, and you could record your audio. And it was really cool. It was really easy. The problem is it creates audio PDF files, which can be problematic, particularly if you have a Mac. But what happens in most browsers is if you open this, you're going to see what I see in my browser. Okay? And you're going to see the writing, but you're not going to see anything else. And that's because most browsers are going to open a PDF file up in a preview program. It's actually not an Adobe Acrobat Reader. It's just a preview program within the browser. Okay? So to get these to work, or at least I think the best way to get these to actually play so you can hear the audio, is to click download. And I don't know if everybody else gets a download link like I do when I open these. Okay? So if you click download, it should download the file to your computer. And this one's still opened in my browser again, even though I downloaded it. So what I'm going to have to do is so what you really need to do is have an Acrobat Reader. Okay. Oops. Let's see. I opened this the other day, so let me see what else we have here. There it is. So this was actually, I downloaded it the other day just to try it, just to make sure that it works. So when you download the program, you need to know where it goes to. And for when I download it, it goes into my download folder, and then you'd have to go there and open that up. But when you open it in Acrobat, Adobe Acrobat, it will look like that. And then you can click play. And it will play the writing, and it will play my audio. Now, I don't have the audio on right now, because sometimes I get feedback when I turn it on with the microphone. You won't be able to hear it anyway. Well, yeah, you can kind of hear me. So that's that actually playing. And you can jump ahead. If you can see the grayed out writing, you could jump to anywhere in there. I thought this was really cool, but again, to get these to play, but they have to be open in Adobe Acrobat, not in your browser. Okay? So I hope that helps. I went away from recording in this format because a lot of students had issues, but I did not want to go back and re-record all of these answer keys before the final. So, Maddie, I know you asked about it, but I don't know if that helped. But downloading it to your computer and making sure you open it in Adobe Acrobat is what you need to do. The other thing you can, if you know how to do the settings in your browser, you can tell your browser to open PDF files with Adobe Acrobat, and it will open within your browser the correct way as well. So either way. All right, let me turn my volume off here. Yes, Kelly? Uh-huh. So, Section 2, about 10 minutes ago, well, maybe more than 10 minutes ago, maybe 20 minutes ago, for Section 2, I did update the ALEX score in Blackboard. So that should be currently up to date. Section 3, since you're, wait, I got it backwards. Gosh, Section 3, you guys have the exam tomorrow, don't you? No, 2 is tomorrow. Okay, I did the right one. So Section 3, I was like scrambling. So Section 2, I did update your ALEX score. Section 3, I haven't done so yet because the final's not till Thursday. God, my brain. Oh my gosh. The Section 3, Section 2 has messed me up all semester long anyway because Section 3 is before Section 2, time-wise. And I just never... Yeah, Section 3 is 11:10 and Section 2 is at 12:45. Don't ask. Anyway, we need to get on track. So the Section 2 grades should be pretty close. I still have to put the office hour points in. But in terms of calculating your grade, you should get a pretty good idea what you need tomorrow. Right, so you need 900 points for an A, 800 for a B, 650 for a C. So take your current total points, subtract it from whatever grade you're shooting for, and that's the number of points you need on the final out of 200. Hang on, folks. I mean, the final exam is going to be important for a lot of you. Okay, it's 200 points of your grade, it's 20%. So you should make sure you know how to calculate the grade going in that you need. Okay, and you might want to check your grades again in Section 2, since they were just updated, so you can see how many points you need on the final out of 200. Yes, Christy? I do not drop the lowest ALEX score, no. I drop the 2 lowest pre-lecture scores and I drop the 2 lowest participation scores. Okay? Yes, Ellen? They are not there yet. Hopefully I can get that done tomorrow morning. Okay? I was typing in the last office hour points today because I had a whole bunch of people come last week and I just didn't get those up there. If you know you have 10 attendances for office and SI, that would increase your grade by 1% from what's in there right now. Okay? Yes, Amy?
So ALEX grade is the overall ALEX grade that you can see on the grade book, right?
I don't know yet because I don't know if ALEX has closed so that it's factoring in your PI score yet. Okay? Your ALEX score is your objective score plus the PI score average together, and I don't know if it's actually doing that. Okay? When I calculated it, now I will do that for Section 3 as well. It's already done for Section 2. Section 3, I need to go back in, re-download the ALEX scores, and post the updated one. But I'll average your objective score in ALEX with your PI score. Okay? Logan.
Tomorrow's my birthday. Can you give me a bit of extra credit on the finals as a present?
Yeah.
Would you like us to sing happy birthday to you during the final?
Sure.
Would that be extra credit? All right. Okay. Remind me. We'll sing Logan happy birthday tomorrow before the final exam. Yes. I can't hear you. I'm sorry. I haven't looked, but when I looked on Thursday, one class was at 70 and the other class was at 69%. So I am assuming that they're both over. Other question back there? Was there another question? Oh my gosh. Look at that. Woo. That is impressive. That's like crazy good. Hopefully the average on the final will be close to that tomorrow. Yeah. That would be nice, but all right. we need to get reviewing. All good questions, but so if you're in section 2, try to be here early tomorrow if you can. Try to be here at least 10 minutes early just so we don't have to rush getting started and whatnot. Okay, section 3 I'll see you on Thursday. So 12:30 tomorrow for section 2, section 3, 10 a.m. on Thursday. Okay, in this room. All right. So in the first 2 review sessions on Friday and Sunday, we went through the first 4 chapters: thermokinetics, equilibrium, acid base. That takes us kind of to our latest material for the semester, which you should still be relatively familiar with. So this was a big chapter for us, lots of material in here. Again, notice that the number of questions that come from each chapter. So this chapter has quite a few questions from it, 10 questions. So it's a pretty big part of the exam. So be able to identify buffers. What are you looking for? Weak acid, weak base that are what? Conjugate pair, right? Okay, so a conjugate acid-base pair, weak acid, weak base. So again, even in Sunday's review session, I talked a lot about you need to be able to identify strong acid, strong base, weak base, salts, and that all then flows into buffers as well. If you don't know what is a weak acid or strong acid, it's kind of hard to identify a buffer. Okay. One thing to watch out for is typically one component of your buffer will come from a salt solution. Okay? Because if it's a charged species, which at least one component of your buffer will be, it's not going to exist as a pure substance. It will be combined with something else. So examples would be something like HNO2 with NaNO2. That would be a buffer. HNO2 should recognize as a weak acid. Okay, it's not one of the 6 common strong acids. And NaNO2 is a salt that contains NO2 minus. So this salt contains NO2 minus and Na plus. Okay, so HNO2 and NO2 minus, there's your conjugate acid-base pair. Okay, another example. That would also be a buffer. Again, dissolved in water. So these are all aqueous. Does everybody recognize that as a weak acid in a conjugate base? Okay, so carboxylic acid is a weak acid. So that's formic acid on the left. And then this salt on the right contains potassium ion, which is just going to be a spectator. But more importantly, it contains the conjugate base of formic acid, okay, HCOO minus. Okay. Also watch, this is a one that you might see on the final. Something like that. Ammonia, what's ammonia? NH3. It's not a weak acid. Ammonia is a weak base. And then that salt contains what?
Weak acid.
Contains a weak acid. So ammonium. So NH4 plus Cl minus. Okay, so we have ammonia, which is a weak base. NH4 plus is its conjugate acid, which is a weak acid. Chloride is not going to do anything. It's a spectator ion. Okay, so recognize a buffer. Be able to calculate the pH of a buffer. How do we do that? What's that? Okay, so the Hasselhoff equation. You can set up a weak acid ice table or a weak base ice table. So if you want to do that, probably the easier way to solve for the pH of the buffer. Okay. On the last exam, I changed it up a little bit and confused some students. I didn't mean to. I thought I was being a little more helpful when I did this on the last equation sheet. And I don't know if I have it this way on the final exam. I didn't even look. Sometimes I'll write it like this. Is that confusing?
Yes. Yes.
That's why they wrote it in Alex? Yeah. So this is trying to show you that the acid part of the pair has one more H plus than the base part of the pair. So I think it's even being more descriptive that it's the conjugate base over the conjugate acid. No, you don't like that? What's that?
I can see it.
Right? So HA is just a generic weak acid, and A minus would represent its conjugate base. Oh, well. All right, I'll look at what I have on there, and then maybe I'll write the other one on the board. I don't know. I guess that's causing too much confusion. All right. One thing to know with this, if base is equal to acid, so conjugate base, conjugate acid, the two parts of the buffer are equal in concentration. What can you tell me about the pH of that buffer? Okay, make sure you know that. We will see that again in a couple bullet points further down, but that's a good thing to know just in general. Because you can, one, if the problem gives you equal concentrations of the two components, you can get the answer very quickly for the pH. But it's also a good check on pH relative. If I know what it is when they're equal, if I have more base, then the pH should be higher. If I have more acid part of the buffer, then the pH should be lower than the pKa value. So it's just a good check. Oh, I forgot to bring example problems. Darn. Okay, I can make up problems. All right, be able to calculate the pH of a buffer after the addition of a strong acid or strong base to the buffer. Hi. Okay. Let's. Oh. Thank you. You guys are so much smarter than I am. I just click close. I don't actually look to see what it says. Yeah. All right. Boy, it's all about extra credit. All right. All right. Calculate the pH of a buffer after you add strong acid or strong base. So let's do this one. Let's say we have you want to add strong acid or strong base to this buffer? Strong acid. A little bit of both at the same time. Well, all right. So let's add strong acid first, then we can see how it would change the calculation if we did the same amount of strong base, if we want to see that. Let me give you one more piece of information. K is 1.8 times 10 to the negative fifth. So one thing you might want to do is calculate pKa, because those two concentrations are equal at the start. They're both 1.5 molar. So let's see what the pH of this buffer is before we do this calculation. Is everybody able to get that pH of the buffer before we start? Yeah, it's 4.7. It's actually 4.7447, so 4.745-ish. Okay, so that's the pH of the buffer. Yes? No? All right. And again, all you have to do, because those concentrations are equal, is just take the pKa value. Now we're going to add strong acid. So what's going to happen to the pH of that buffer?
Decrease.
It's going to go down. Okay, it's going to become slightly more acidic. Okay, so again, you're doing a multiple choice test. You can probably eliminate a couple of choices that are there. If you know, oh, I'm adding strong acid, the pH has to go down. All right, next thing. We are adding strong acid. What part of the buffer is it going to react with? The base. Now, what is the base part of that buffer? Okay, so the salt contains the base. I would leave the sodium alone. That's just going to be a spectator ion. Remember, this salt is actually going to break apart. So in solution, it actually exists as Na+, hydrated by water, and then the anion would be CH3COO-, hydrated by water. Okay? So the sodium ions aren't doing anything. But again, the acid part of the buffer has one more H+ than the base part of the buffer. It's a conjugate acid-base pair. So this is my base. Okay? And again, this is a weak base. So we do need to get our reaction correct. So the acid does what? Donates a hydrogen ion to the base. We will produce the conjugate acid, which is the other part of the buffer. And then we do also get some chloride ion, which is just a spectator. Conjugate base of a strong acid is not going to do anything. Yes?
You had a question. I was asking which species are left or something. Is that like CL and
That was in Alex, yeah. There was a question in Alex that asked, what, after you did the reaction, what did you have in solution? Or something like that. We will talk about, certainly at the equivalence point, you need to know what's in solution. For a buffer, for the most part, you're still going to have both buffer components left. The amounts of the buffer are going to change, but you're going to have both buffer components left. That's the most important thing that's in the solution. Okay? All right. So let's assume that the volume doesn't change when we add the strong acid. Okay? And that way you could work with molarity or moles. Let's just go ahead and work with molarity, since most likely the problem will say assume the volume doesn't change when you add the strong acid. So we have 1.5 molar, 1.5 molar. What is the molarity of the HCl?
0.25.
So moles, 0.5 moles. That was added to 2 liters of the buffer. So 0.5 moles divided by 2 liters. So 0.25 molar. How much reacts?
all of HCl?
All of it. Okay, so even though this is a weak base, HCl being a strong acid is going to donate all of its hydrogen ions. So this reaction goes to completion. We do have a limiting reagent, which is the HCl. It's nice, all mole ratios are 1:1. After reaction, all the strong acid is gone. Okay, that's why this buffer has worked. The strong acid has been removed from solution. The pH will change though because the concentration of the base has gone down. The base part of our buffer has decreased and our acid has increased. Okay, so now we have more acid part of the buffer and less base. So we're definitely going to be more acidic. So what do we do with those new concentrations? Plug them into the Hasselhoff equation. So let's just try to do that here on the side. Okay. We calculate the pKa value at the start of this reaction, so we know that. Oh, 4, sorry. Got ahead of myself there. Okay, make sure that you get the right concentration in the right place. This is the base part of our buffer. It reacted with the acid. And this is our acid part of the buffer. So it's 1.25 over 1.75. This comes out to about 4.60. I end up like 4.599. Is that about what you expect? It's always good to take a look at your answer and at least say, does it make sense? This is a buffer, so we don't expect the pH to change too dramatically. It went from 4.74 down to 4.60, so it appears our buffer has worked. And because we added strong acid, the pH should decrease. Questions? No questions? All right. So let's very quickly just look at what the difference would be if we added the same amount of strong base. So the same buffer. Okay, so let's add 0.5 moles of strong base, potassium hydroxide, to 2 liters of that buffer. Now I'm just going to represent my strong base as hydroxide. Potassium hydroxide is a soluble salt. It will ionize to potassium ion and hydroxide ion. Potassium ion doesn't do anything. It's a spectator. So what's going to react is hydroxide. That's strong base. So what part of the buffer does that react with? Acid. So here is our weak acid part of the buffer. Acid donates an H+. When it loses the H plus, we produce its conjugate base, which is the weak base part of the buffer. And we will also get some water in this case when hydroxide gains that H plus. Okay? So again, you see the two buffer components. One is going to react. We're going to produce the other component of the buffer. Okay? Now, we added strong base, so what should happen to our pH? It should go up. Okay, it should increase. And that's because the weak acid is going to decrease, and we're going to make more base part of the buffer. Now, these are the same numbers, so this is going to look pretty similar. These were 1.5 molar at the start, 0.5 moles divided by 2 liters, 0.25 molar hydroxide. Strong base is going to grab every hydrogen ion it can. This reaction goes to completion. Oh, sorry. I jumped to the end without writing minus. So all the strong base will react, 1-to-1 mole ratios. After reaction, all the strong base is gone. Our acid has decreased because it reacted with the base, and we have produced the base part of the buffer, so that's gone up. Okay, now you can see our numbers are the same as our last ice table, but it's now the base that's larger and the acid that's smaller. So when we plug into the Hasselhoff equation, it is base over acid. Okay, so take a look at your previous calculation. Again, I used the same numbers, but in the previous calculation it was 1.25 for the base and 1.75 for the acid. Okay, where in this one, they are the opposite. The base has gone up, the acid has gone down. So this one, we end up with a pH of about 4.89. About what you expect? Yeah, we added strong base. The buffer should resist change in pH, so it shouldn't change too much. We went from 4.74 up to 4.89. pH increased. Kelly? Right. So for buffers, I mean, this equation fixes that the pH is equal to the pKa plus log of base over acid. So for a buffer, at least if you're using the Henderson-Hasselbalch equation, you're always going to use pKa. Okay, now I think what you're talking about from last night is we were looking at a salt solution. And the salt solution contained the conjugate base of a weak acid. And so that conjugate base is a base, so we needed its Kb value.
So if it's like a base is on the left side, use the Kb, then it's...
Right. And that's, so a buffer is different. A buffer, you have both components. You have both the acid and the base. But a salt solution is just going to have one component. Okay? But yeah, you do, in general, you have to look at what you're reacting. Is it a weak base or is it a weak acid to decide whether you're using Ka or Kb. But for buffers, it's always going to be Ka because this is the pKa value. All right. How do we choose an appropriate indicator for a particular pH? What do we look at? Yes, Jeremy? Yeah, that's a titration, so we'll get to that in a minute. But so let me give you a couple of different choices. Let's say we have, well, I'll just give you two choices. So let's take the buffer that we just had. So kind of a nice symmetry there, actually. Acetic acid has a Ka value of 1.8 times 10 to the negative fifth. Ammonia has a Kb value also of 1.8 times 10 to the negative fifth. Which would be better to prepare a pH 9 buffer? Okay, what do we need to calculate? Yeah, we really need pKa, right? Okay, so for a buffer to be effective, you want both components of the buffer to be present. You want both the weak acid part of the buffer and you want the weak base part of the buffer. Okay? They don't have to be equal in concentration, but that's a good place to start, just to see what is the pH of that buffer if the two components are equal. And we've already talked about that. We know that if the two components are equal, pH of that buffer is equal to its pKa value. Okay? Now we already calculated pKa for this buffer, and we got about 4.74. If you calculate pKa for the ammonia-ammonium buffer, what do you get? Yeah, somewhere around 9.26, 9.25, somewhere in that range. Okay, now realize this is a Kb, so you're going to have to get the Ka value first, and then take the negative log, and that you should find a pKa of about 9.26. So 1 times 10 to the negative 14th divided by the Kb. Yeah, about 5.56 times 10 to the negative 10th. That would be the Ka for the acid part of the buffer, which is what we need. So the Ka here is 5.56 times 10 to the negative 10th. Now take the negative log of that to get the pKa. And yeah, it's like 9.255, so 9.26. Okay, so make sure you can do that. It's an important thing to calculate. Again, this pKa value tells us that the two components are equal. So this buffer, is going to be pretty good around pH 9. The acetic acid buffer, which is the one at the top, would be a terrible buffer at pH 9. To get that buffer to pH 9, you would just pretty much have to have all base and almost no acid, which really wouldn't do you any good. So this buffer would be good, or in the 4.5 to 5-ish range or so. Jesse?
Does that buffer have a plus or minus?
Yeah, I typically say about plus or minus 1. If you go plus 1 or minus 1, you've reduced one part of the buffer down to 1/10 of what the other part of the buffer is. So you certainly wouldn't want to go any more than plus or minus 1, because then you're reducing one component too much. Okay? All right. Be able to calculate the ratio of base to acid or acid to base needed to prepare a buffer of a particular pH. What are we going to do for that? the Hasselhoff equation as well. So there's your ratio of base to acid. Okay. So for this type of problem, you want to prepare a particular pH, so you will know pH. You'll be given the Ka value or the Kb value, so you can get pKa. So you're just going to have to solve for base over acid. Okay, so it's a pretty easy calculation. Don't forget about this log term. Okay, so we could do a quick calculation. Let's say we wanted to prepare a, let's take this, let's take this buffer. Let's say we do want to prepare that pH 9 buffer. Okay. Okay, so pH 9. pKa is about, and this is rounded, but let's call it 9.26. We just calculated that up here. All right, how do we get rid of the log term? Yeah, 10 raised to that power. Oh, I somehow keep getting the same number that was on the last exam too. So we're going to get 0.55 is equal to base over acid. And again, that would be 0.55 to 1. Okay, so this says we need more acid than base. Is that what you expect? Should we need more acid part of the buffer than base part of the buffer? Why do we need more acid? It's a lower, this pH is lower than the pKa value. So again, that 9.26 is when the two buffer components are equal. If we want to make, even though pH 9 is still a basic pH, we want to lower the pH from 9.26. We're going to need more acid part of the buffer, which is what this tells us. Our base is 0.55 to 1 for our acid. Now, what if I ask this as ratio of acid to base? Oh, Jeremy's saying don't do that. Get it wrong for the third time in a row. Don't get it wrong for the third time in a row if it's acid to base, because it's not. You're almost done. If you want acid to base, you do what? You just flip it. We're taking the reciprocal, or the, what's that? Yes. Yeah, so acid to base, you're going to take 1 divided by 0.55, you're going to flip it, so 1.82 or 1.8 to 1. Okay? So that again shows us we need almost double the amount of acid part of the buffer as base, 1.8 times more. All right, good with that? All right, strong acid, strong base titrations in detail. Okay. So typical problem would just have you calculate the pH at the start, which I think most of you can do. You're just going to have strong acid or strong base, depending on how you do the titration. So let's calculate the pH somewhere else in the titration. Oops. I want to do that. See if I can get this to work. All right, so let's take So we're going to take 50 milliliters of 0.2 molar nitric acid, titrate that with 0.5 molar potassium hydroxide. Calculate the pH after 30 milliliters of KOH have been added. Okay, so we're starting with strong acid. We're going to add the strong base. Calculate the pH after we've added 30 milliliters. All right, so it's always good to have a correct reaction. This one's pretty easy. There's our strong acid, HNO3, our strong base, potassium hydroxide, H plus from the acid. It's going to be gained by hydroxide from the base to produce water. And then we also get potassium ion and nitrate ion, which is the salt that is produced. Okay? Now, when we add the strong base to the acid, the volume of the solution changes. So we should work with what? Moles. We should work with moles. Okay? So HNO3, so molarity times liters. This is just rearranging the molarity equation. Molarity times liters is equal to moles. So 0.05 liters times 0.2 molar. So 0.01 moles for HNO3. 0.5 molar times 0.03 liters. Okay. Is everybody okay with that? Molarity times liters gives you moles. So at this point, we have more moles of base than acid. So it's certainly going to be a basic pH that we're going to calculate here. So how much reacts? All the nitric acid. So this reaction clearly is going to go to completion. It's a strong acid, strong base. The acid is going to donate all the H+. The base is going to accept that. This goes to completion. HNO3 is our limiting reagent. All the strong acid is gone, and we have excess strong base, 0.005 moles. So what do we do with that 0.005 moles? Divide by the total volume in liters. So 50 milliliters started with. We added 30, so 80 milliliters. 0.08 liters. .0625 molar. Now be careful here. That is strong base. So this is the concentration of potassium hydroxide. But what do you know about a strong base? It completely dissociates into ions. So this will also equal our hydroxide concentration. Let me get a little bit more room here. So hydroxide is also equal to 0.0625 molar. So what should we calculate from that? POH. So take the negative log of that. POH is about 1.204. Subtract that from 14. Well, let's call it, I don't know how many sig, I think we only had 2 sig figs, so let's call it 12.80. Okay. Is that about what you expect? For this point in the titration, we only did 1 point in the titration, but at this point we're at where we've gone, if we started with the acid in the flask and we've added that much base, we've gone by the equivalence point, we now have excess base, so our pH should be pretty basic. Okay? pH at the equivalence point for this one? What would the pH at the equivalence point be? This one would be 7. This is not the equivalence point, but at the equivalence point, this is what we would have in solution at the equivalence point. We would have that salt in water. And that salt containing the conjugate base of a strong acid is not going to affect the pH of that solution. We'll talk a little bit more about that in a little bit. All right, any questions on strong acid, strong base titration? Another thing that you'll probably see is something like molar mass or mass percent from a titration. Okay. So let's do a molar mass one. Let's say we have and I'll give you the mass of the acid in just a minute. I'm going to make up a number in just a second. Let me just double check that really quick. Okay, that'll work. All right, so we're going to weigh out 0.0907 grams of an unknown acid. It is a diprotic acid, H2A, and it's titrated with 0.1 molar sodium hydroxide. It takes 18.5 milliliters of sodium hydroxide to neutralize the acid. Calculate the molar mass of that unknown acid. So what should we get first? Okay, so we can get moles first. I would start with something else. Balanced equation would be good to know. Now, you can get the mole ratio between the acid and base without writing out the whole reaction. Not that this reaction, we're going to get water and a salt produced, but the reaction here is for every 1 H plus, we need 1 hydroxide. Okay, so that's the real reaction, H plus OH minus. This is kind of the net ionic reaction. H plus from the acid combines with hydroxide from the base to produce water. So it has to be 1-to-1 H plus to OH minus. So if I have 2 H pluses, I need 2 OH minuses, 2 hydroxides. So what's my coefficient here? 2. Needs to be 2. So there's my mole ratio without writing water and salt on the other side. I mean, we could do that as well. So the next thing I already heard, we need to get moles. So we have volume. We have molarity of the base. We want to get molar mass of that acid. So we need grams of that acid, and we need moles of that acid. Okay, so this is molar mass of the acid. Grams we're going to weigh out. Okay, so we have that, but we need to find moles. Calculate the molar mass. So molarity times liters. Okay, so divide by 1,000 to get to liters. That's NaOH. We need moles of acid. Divide by 2. So we have to set up our mole ratio. Okay, so looking at our balanced equation, 2 here, 1 there. Okay, so this is stoichiometry. We use molarity in liters to get moles of one thing in the equation. We then use the mole ratio to get the moles of something else. And then what do we do with that moles of acid?
Grams divided by the moles.
Grams divided by the moles. So our molar mass of the acid, the grams, is given in the problem. If you were in the laboratory, you would weigh out the unknown acid, so you would have that value. Grams divided by moles will give us the molar mass.
98.1.
About 98.1, exactly right. What? Writing over what I just have written?
No, he put 98.05, so you got it wrong.
Oh, I got it wrong? Okay, well, sorry. It's a multiple choice test. I would still get it right. Right? Okay. We good with that? Yes.
I know it's really small and negligible, but if we have something other than H2A or whatever, do we need to calculate the molar mass for like the other elements in there as well?
Well, you don't know what that is,
Okay.
right? The A is just generic conjugate base.
Okay.
So you would know what that molar mass is. So you're actually, so we're not giving you the formula of the acid, so you actually have to solve for it. Okay? Okay. Yes. Well, mass percent is going to be done in a similar manner. So you actually probably tried to block this from your memory, but Chem 151 lab, experiment 6 and the lab practical was mass percent of an acid in an unknown. Everybody remember that? So you were given a mixture which had a certain percentage of unknown acid in it, and the rest of the mixture was something else. Okay? So mass percent of acid in an unknown would be mass of the acid divided by the total mass, which is the sample mass, which you'd weigh out. And then you multiply by 100 to get a percentage. Okay? So you would know this. In the lab, you'd actually go to the lab and you'd measure out how much of that mixture you had. In a problem, the mass of the sample would be given, the total mass. So you would do the same calculation, assuming it was a similar problem. You do the same calculation, you would get moles of acid as we did here. But then you need mass of acid. So this one you'd have to know what the acid is so you could get from moles to mass. Okay, so there would be another step here where you'd have to take the molar mass of that acid and convert to grams. Okay, so this problem's a little bit different. You actually know what the acid is, so you would know its molar mass, but it's a mixture, so only part of that mixture is acid, and you're trying to find out what percentage of that mixture is acid. Okay, so there's kind of one more step. You would still do molarity times liters to get moles for the base. You would then do the mole ratio to get the moles of acid, and then you'd have to use the molar mass to get to the mass of the acid, and then divide that by the mass of the sample. Okay, they're very similar. It's just a little bit different in how you solve for it. Okay, there was a mass percent one just recently on one of the exams. I don't know if it was the retest or if it was exam 3, it was very recent. I don't know. All right. How do we choose an appropriate indicator for a titration? Or let me ask that a different way. At what pH does an indicator change color? Well, it's called the endpoint, so the color change is called the endpoint. But it depends on you've seen indicators in the lab, right? They change color at different pHs. Phenolphthalein changes about pH 8-ish. Bromethymol blue is probably pH around the same. It's somewhere in that same range. But there's all different ranges for indicator. So at what pH does a particular indicator, just in general, not a number, but at what pH does an indicator change? Of the indicator, yeah, and so it's kind of like a buffer. So an indicator here, and I didn't spend much time in class on this at all, but an indicator in water is a weak acid. So this is just some generic indicator, some generic weak acid. So in water, it's going to produce hydronium and its conjugate base. Okay. Well, it turns out that an indicator, the acid part of the indicator has a certain color. Or maybe not. Phenolphthalein is colorless acid, but a certain color. And then the weak base part of that indicator has a different color. Okay, so an indicator is really just a weak acid and its conjugate base, but they have different colors in solution. Okay? So the indicator is going to change color centered around when you have both components present in solution. There's going to be a range, but so when would the two components of that indicator, the acid and the base, be equal? When's that? Well, hopefully we've chosen the right indicator that it changes color at the equivalence point. But think about a buffer. If the two components of your buffer, because in effect, we're going to have the weak acid part of this indicator and the weak base part of the indicator together at some point in the titration. If those are equal, what's the pH of that?
About 7.
It's not 7. pKa. Okay, so just like a buffer, so this is a conjugate acid, conjugate base pair. If those are equal, okay, so that's why different indicators change color at different pHs. Okay, it's because they have different Ka values, and it's going to change color centered on its pKa value. Now, there will be a range, typically like a buffer. The color change will go over a range that's typically about 2 pH units. So if you had a pKa of 9, that indicator is probably going to start changing color about pH 8. It's going to change over a range of pH. Okay, so like a buffer, for an indicator, you just need to calculate the pKa. So that's pretty simple. All right, what is the net ionic equation for a strong acid, strong base titration? What's the real reaction that happens in an acid-base titration? So let's go back up to the titration we just looked at. Where's our strong acid, strong base titration? It's further away. All right. So here's our strong acid, strong base titration. What's really happening in that solution? Well, we produce a salt and water, but what's the real reaction? So that's a net ionic. The net ionic, you boil it down to what is the real reaction going on there.
H plus OH plus H2O.
Right. So H plus from the acid combines with hydroxide from the base to produce water. That is the net ionic. That's the real reaction. H plus from this acid, hydroxide from the base to produce water. Okay? So that is okay. Yes, there is salt present there as well, which can be important in determining the pH. But this is what, these are called neutralization reactions. You're neutralizing the acid with the base. That is the net ionic equation. H plus from the acid, hydroxide from the base. All right. pH at the equivalence point. We already did strong acid, strong base titration. pH is 7. So at the equivalence point of these two titrations, let's figure out what determines the pH and whether the pH will be acidic or basic. So the first one. Okay, so I hear most people saying basic. Weak acid with a strong base. The pH will be basic. H plus from the acid combines with hydroxide from the base to produce water. Okay, but we also have Na plus, and then the conjugate base CH3COO minus. I'm going to put a comma here because those aren't going to be together. Those are going to separate from each other. It's going to dissolve, dissociate. So at the equivalence point, at the equivalence point, the acid is gone, the base is gone. We've added just the right amount of base to completely react with the acid. So at the equivalence point, all we have is salt dissolved in water. And so there's our salt, Na plus CH3COO minus. Is sodium ion going to do anything?
Nope.
No. What about acetate ion, CH3COO minus? We'll make it more basic. That is the conjugate base of a weak acid. So this is, let's write it up here, conjugate base of a weak acid. So here's your weak acid over here. That's its conjugate base. So a conjugate base of a weak acid is what? It is a weak base. But it is a base. So it will make the solution basic. For this one, pH will be greater than 7 at the equivalence point. All right, next one. Weak base, strong acid. It's going to be acidic. pH will be less than 7. Let's see why. H plus from the acid donated to the base. We're going to get NH4 plus, the conjugate acid, and Cl minus. What about Cl minus?
No strength.
No base strength. Conjugate base of a strong acid. Again, the stronger the acid, the weaker the conjugate base. So conjugate base of a strong acid has no base strength in water. What about NH4 plus?
Conjugate acid of a weak base.
Conjugate acid of a weak base. Okay, so this is conjugate acid of a weak base. Here's your weak base right there. And so the conjugate acid of a weak base is what? It is a weak acid. So it will be acidic, pH less than 7. Okay? So strong acid, strong base, pH is 7 at the equivalence point. Weak acids, the top one, weak acid with a strong base, it will be basic because of the conjugate base. Make sure you know why. And then this one, a weak base with a strong acid, will be acidic, but it's not because of the HCl, it's because of the conjugate acid of that weak base. Okay? All right, we're almost done with this. Is a long, as you can see, this is a long chapter. All right. Last thing in this chapter, we did a little bit with solubility. What do we mean by an insoluble salt?
Dissociates partially.
Yeah, partially dissociate. So soluble salts we assume completely dissociate into ions. Insoluble salts aren't truly completely insoluble, but they don't dissolve very much. But a little bit will dissociate into ions. So just kind of know what we mean by that. Be able to calculate molar solubility. From KSP. Do we know how to do that? Should we do a calculation? Okay. Let me, let's do, since I didn't bring a textbook with me. Let's go to the Google. Oh, come on. 1.4. Well, and should we trust this KSP value you find online? I don't know. We'll call it good. Okay. So you're given that KSP value. All right, so what do we do with that? It's taking a long time. Okay, so we have to write the equation of this salt dissolving in water. So lead iodide is an ionic solid, it is a salt. It does not dissolve particularly well in water, but salts, a soluble salt completely dissociates. This salt will only dissociate a small amount to its cation. And then how many anions? We have two iodides. Okay? Now, if you don't get these charges right, you can still solve this problem correctly. Okay? But it turns out iodide's -1. That means that lead must be +2. All right, initial amount of the solid, does it matter? No, as long as we have some present, before it dissolves, our products would be 0. We are not going to get much product, but we will get a little bit. Plus X for lead 2+, and what about iodide? 2X. And at equilibrium, the solid is not going to enter into the expression. Lead ions will be X, and iodide will be 2X. All right, what next? Yeah, set it equal to your KSP value, products over reactants. Here we don't have to worry about our reactants, solid and liquid, so we only have to worry about our products. So our KSP, which is 1.4 times 10 to the negative 8th, is X times 2X. What do we do with that 2X? Squared. So that coefficient of 2, you see in the 2X term, and you also see it again here squared. So don't forget that. So this will equal to 4X cubed. Oh, great. Computer's running so slowly right now. All right, so divide by 4, take the cube root. Get an X value of 1.5 times 10 to the negative 3. And what is the unit on that? That is molarity. So that is your molar solubility. So that X value is your molar solubility. Okay. Let's do one more real quick. What if instead of pure water, this was... So this one was pure water, but what if it was in 0.1 molar lead nitrate? What would that change in our ice table? Okay, the initial concentration of lead would not be 0. Okay? So in pure water, maybe not tap water, but in pure water, lead concentration should be 0. Okay? But if you're dissolving that salt in a lead nitrate solution that's 0.1 molar, this would be 0.1 molar at the start. Okay, that's what's called a common ion. So your calculation would be very similar, except your KSP value, your KSP would still be the same. But we would now have Should have left myself a little bit more room here. Point 1 plus X. Okay, it was just X in pure water, but now we have that extra lead ion from the lead nitrate. And what do we do with that 0.1 plus X? Small x approximation. So this is just going to become 0.1 times 2x squared. Okay, and so this is 4x squared here. So let's solve this. 1.4 times 10 to the negative 8. We divide by 0.1, and that's 4x squared. Divide by 4, square root. We should get an x at 1.87 times 10 to the negative 4th molar. Did I do that right? Okay. So what happened to our solubility? It decreased. So adding a common ion is going to decrease the solubility. You should probably know that. So again, this is a Le Chatelier's problem. He just won't go away. We, in effect, added lead ions. If we add lead ions, it's going to shift to remove it. It shifts to the solid. Less of the solid is going to dissolve to ions. So adding a common ion decreases the solubility. All right. It seems like we just can't get out of this chapter because there's really one other thing in here. Because we need to get to electrochem. Boy. What should we do? We're not going to make it through everything. Skip it for now. This will probably be on this last one, on this chapter. If you mix two solutions, will precipitate form. That was on the exam 3 and on the retest, so you should probably go back and look at those. That's where you have to calculate Q and compare Q to K and see what's going to happen. So you might want to go back and look at that problem. But let's get to some electrochem since we haven't spent any time with this. Assign oxidation numbers. Let's just do an example. What is the oxidation state of manganese in permanganate, MnO4 minus? What is the oxidation state of manganese?
+7.
Oh, that was quick. Okay, so remember certain things you're going to know. Oxide is -2. Hydrogen ion is +1. Alkali metals are +1. Alkaline earth are +2. Fluoride's -1, and so on. So we can figure out this whole ion is -1 overall. Each oxide is -2. So -2, and there's 4 of those, so we have a total of -8 for the oxides. Oh, that's -8. Okay. So to end up with a -1 overall, what must manganese be? +7. Okay. So that's assigning oxidation state. Again, you pretty much will be able to kind of figure out one thing based on what other things are that you know: oxide, hydrogen ion, alkali metals, things like that. Okay. Balancing redox. Let's get an example here. Let me just look at this table. Okay, let's balance that. It's a pretty easy one, but this will give you an idea of what we need to do. So there's the reaction we're going to balance. So what do we need to do with that? Separate it out into half reactions. Okay. Actually, let me get this down onto the next page. So clearly silver ions go with silver, and MnO2 goes with Mn2+. Well, actually, I think I got this backwards. Hold on. Let me see. That's +4 +2. That's gain. Okay, hold on. I have two reductions. That's not going to work. See what I get for making up a problem on the fly. Let's do this. So let's switch our silvers. Okay. Sorry about that. Can't have two reductions. We need a reduction and an oxidation. All right, so let's balance the silver one first. That one's really easy. What do we need? All we need is one electron. So silver metal, an element, is neutral. To balance that, all we need is one electron. Okay, to balance a charge. We have +1 and -1 equals 0 here. All right, other reaction. Manganese is already balanced. That's good. So then we go to oxygen. What do we need for oxygen? 2 waters. So 2 oxygens, 2 oxygens. So we had 2 waters. We now have 4 hydrogens. 4 hydrogen ions. Okay, and 2 electrons. So this side is +4. So the 4 hydrogen ions. This side is +2. It's a difference of 2 in the charge. So 2 electrons. It needs to go on this side. So 2 electrons and 4 plus, -2 and +4 equals +2. So this first one is our oxidation. Silver metal lost an electron to go to silver plus. This second one is our reduction. Oops. All right, what next? Yep. Balance the electrons. Electrons gained and lost must be equal. This reaction can't gain 2 electrons if that one only loses 1. Okay, so we have to multiply the top one by 2. Now we can add them together. We have 2 silver, metal. We have 4 hydrogen ions. We have manganese 4 oxide. We have 2 silver ions. We have manganese 2 plus. And we have 2 waters. Did I get everything? That's an H plus. Good? Is it balanced? Yeah. So the quick check, this is not a very particularly hard one, 4 plus, and that side's 4 plus. If your charge balances, you probably did it right. You can then go and count the atoms as well. Okay? So that's balanced in acidic solution. I'll be nice to you. I'll tell you the one on the final is acidic. So to save time, we won't do basic right now. How's that? Okay? All right, questions on that before we move on? Okay. What does galvanic cell mean? Spontaneous. It's spontaneous electrochemical cell. Galvanic is spontaneous. What happens at the cathode? Reduction at the cathode. What happens at the anode? Oxidation. So those The cathode and the anode are the two electrodes of the electrochemical cell. That's where reduction and oxidation takes place. Be able to calculate a standard cell potential. Can we do that? Why don't we calculate it for what we just balanced? So let's find silver. There, where's silver? It's about 0.8. Where is it? Oh, it's not. It didn't go far enough up. There's silver. That's the reduction for silver. What did we have for that half reaction? It was the oxidation, so you're going to need to change the sign of that. And here's the MnO2 reduction. Does everybody see this one right here? MnO2, 4H plus. That's 1.23. That one we did have as a reduction in this reaction. This one was not a reduction as we did in class. This was an oxidation. So that's going to be negative 0.8. Okay, so it looks like we have 1.23 and a negative 0.8. So when we go back, so for this up here, sometime today. All right. Negative 0.8 for the silver. The reduction was 1.23. Just add those together. That's an equal. So what is that, about 0.43 volts? Positive. Spontaneous? Yes. So positive cell potential, spontaneous. That would be a galvanic cell. So I lucked out when I just picked one. Ended up with a spontaneous cell. Okay. If we had this cell potential, how would we calculate delta G? So this cell potential we just calculated, let's stick with that same reaction. If I wanted delta G for that, I guess we're talking signs too, but we'll get to the sign. How would I calculate delta G? You don't have to memorize this equation, but make sure you can do this calculation. So you do need the standard cell potential. We just solved for that. What is F? It's a constant, so that'll be on the equation sheet. That's Faraday's constant. What is N? Moles of electrons transferred. So in the reaction that we just looked at, what would our N be? It would be 2. So we had 2 electrons gained, 2 electrons lost. Once we multiply by 2, that would be an N of 2, 2 electrons transferred. Okay? So that's a pretty easy calculation. You would just, once you had the standard cell potential, you would just plug this in. You would plug in that constant for the reaction that we just did, N was 2, and you would solve. Yes? Yeah, on the equation sheet it'll be 96,500 for Faraday's constant. It'll be there. Yeah, you don't need 5 sig figs for that number or whatever there was. All right, let's talk sign convention for that. So if we have a positive cell potential spontaneous, what are you going to get for delta G? You're going to get negative. So if this is cell potential is positive, delta G will be negative. So make sure you know your sign conventions. And K will be what? K will be large. Okay, so both positive cell potential, negative delta G. spontaneous product favored at equilibrium, we're going to end up with a large K. Okay? The equation that you would need to then go to the equilibrium constant from the cell potential, let's write that in here. Okay, again, that will be on the equation sheet. Okay, but that's how we could go and kind of put these together. So with a positive cell potential, we're going to get a negative delta G. We could take that same cell potential, plug in that same N, and solve for K. And K will be large.
Where did you get the 0.0257 from?
That's just it's a constant that comes out of the equation. This is at 25 Celsius, which is most likely what we're going to be at. So this is actually some values that are plugged in. It's actually RT over NF. So the gas constant, the temperature, N, and Faraday's constant. If you plug RT and F in, you get that constant there. Okay? But that'll be on the equation sheet. Everybody know how to use this equation? So again, if you have cell potential, just plug in, solve for K. Watch for this natural log term. You might have to get rid of that in front of your K.
So for the number of poles with Dr. Last equation, if you multiply the two half fractions by like say 2 and then by 3, would the number of poles in that equation end up being 6?
Well, yeah. So I mean so if you had a half reaction with 2 electrons, a half reaction with 3, you would have to multiply to get those equal.
Okay.
Yeah. So in that specific case, it would be 6. This particular example, we did have to multiply this one. One of them was 1 electron, the other was 2. We multiplied, but that one would just be 2. Okay. Other questions on these? Okay. And so know the sign conventions, know what the magnitude of your K means. Did that. We already talked about anode and cathode. Reduction, oxidation. One thing that, again, I was rushed in this chapter, I would have liked to have a full extra lecture. One thing that you do need for a galvanic cell to function properly is a salt bridge. You need some way for charge to flow, because as electrochemical cell starts to run, electrons are going to flow, so one side of the cell gets negative, the other side gets positive. And so you need something to counterbalance that charge. And the way you do that is you use a salt solution to do that. And the salt ions can flow back and forth to balance out the charge. So a salt bridge is necessary for a galvanic cell. And so make sure you know that. You might see that on the final. All right. And the last thing in this chapter, I mean, we kind of went pretty quickly here. Definitely know how to do the calculations up above, but the equations will all be there. Non-standard cell potential. So all of this stuff up above was standard. There is an equation. I think it's negative. It's negative. Or is it positive? I'm just trying to think. I'm trying to have all these memorized, but I don't think there's a negative here. I think it's positive. Is it negative? Gosh darn it. I had it right. Delta G is delta G plus RT ln K. Oh yeah, you plug in the negative NFE. That's where the negative comes from. All right. That'll be on the equation sheet. So you don't have to worry about a sign. So this equation, most likely you would calculate the standard cell potential as we just did. You would know your N value. What is Q? Okay? And then you would have your standard cell potential. And you could solve for this guy. Okay? So let me see if there's one on one of the practice finals we can take a look at. So we can get a little, oops. There we go. Just to see what a problem like this might look like. So problem 50 on one of the practice finals. You're given a standard potential for the reaction is 0.966 volts. So it gives you the standard one. What would the potential be if chloride is 0.001 and chromium 3 plus is 0.04? Okay. So there's that same equation, the Nernst equation. This one you did not have to calculate the standard cell potential, it was given. What's N for this reaction? 3. So the easy one to look at is chromium going to chromium 3 plus. Okay, you know, we could also figure it out from the silver as well, but the easy one that just jumps right out, chromium metal is neutral, and it goes to chromium 3 plus, so it must be 3 electrons. So it goes from 0 to plus 3. That must be 3. Natural log. Now be careful, solids do not enter in. So don't have to worry about chromium. Don't have to worry about silver chloride. Don't have to worry about silver metal. So all we have in our Q expression is chloride cubed and chromium 3 plus. That's all that's there. All the solids don't go in there. And so this part of the equation becomes natural log of 0.001 cubed times 0.0441. And we still have all right, so 0.001 cubed, 0.0441, natural log. So for all of this on the right, 0.2057 divided by 3, natural log of that, I got a negative 0.204. Okay, but we have a negative sign here, so we're going to add that. I come up with 1.17 volts, which I hope I'm right. Okay. So that's the Nernst equation. That's taking the standard cell potential and getting a cell potential under other conditions. Questions? Yes?
So Q is products times reactants?
It's products over reactants. This one, there were no reactants in it. See that both reactants were solids. So this just ended up being 2 of the products. But yes, normally it'd be products divided by reactants. But in this case, both the reactants were solid. All right, we're almost done, I think. So, sorry, we kind of went through electrochem pretty fast, but look back through that material. Practice some of these on the practice final and using these equations. They're not that bad. The last thing for tonight, you will see a couple of calculations with nuclear reactions, but they're just first order kinetics. And we've already, in a previous review session, talked about first order kinetics. But the first order kinetics equations that you would need that is one of the form of the first order integrated rate law. Okay, that's just another rearranged version of the first order integrated rate law. Okay, and another equation you should be familiar with when you get to these nuclear ones where you're trying to find out maybe how old something is or what the concentration is at a later time. The half-life equation as well. Okay, so quite often you're going to use this half-life to solve for the rate constant that you will then plug in over here. Okay, this is the equation. You might get a question, how old is something? You're going to solve for time. Okay, so if you get a problem in the final that says how old is this artifact or whatever, you're going to solve for time. Okay, this equation I think is easier to use if you want to solve for concentration or amount. These won't be concentrations, but amount at a later time. Concentration at a later time. Okay, so we've already talked about first order integrated rate law. There will be, those problems will be set up as nuclear ones, but it's the same thing. Okay, now the very last thing, make sure you can balance a nuclear equation. They're actually quite easy. You just balance atomic number and mass number. Let's see if there's one on here. Oh, that one's really easy. Let me see what the other final looks like, if there's a better one on it. Lots of stuff, huh? Oh, these are both beta particles. Oh, well. We'll do this one. All right. So this, there's not going to be a gamma ray. Oh, actually, I should write it on the other side. Gamma ray is just high energy electromagnetic radiation. So that has no charge or no mass. You won't see that on the final. We didn't really talk about that. But all we have to do is balance this atomic number, mass number. You might have to use a periodic table. Antimony, SB, where is it? 51. No, I can't see these dark periodic tables. Is it 51? There, I mean, it's right under arsenic. What is it? 51. Thank you. You will have a periodic table on your final exam and an equation sheet. So that's 51. So our atomic number needs to add up to 51. So atomic number of X must be 52. 52 and a minus 1 is 51. And then mass number is the same, 122. So element 52 is going to be TE. So this is TE 122, which would be choice C. Okay? So there'll just be one of those. It'll be just balance atomic number, balance mass number, and you should be good. That's a lot. What's that? There is more. I know. I kind of shortcut there at the end, but go back and go through these practice finals. Hopefully you'll be able to get the audio PDF files to play if there's ones you have questions on, so you can go look at those. You do have to download them. Yes. Yeah, come on down. That'll be easier.
I always get like confused on these. Like, you know how you found out all the charges or whatever?
Yep.
So this was, you said 8?
-8. So oxide is -2, but you have 4 of them. So that's -8. Okay, and then that added with whatever that is has to equal to -1. It's equal to -1, yeah.
So that would be 7?
Mm-hmm.
Okay. Okay, thank you.
Okay. Hey,
Just making sure you got
you're going to come tomorrow, is that right? Yeah, that's fine.
Okay. Do I just like on the Scantron just put section 3? Or like,
Yeah, or when you come turn it in, just let me know. I mean, I'll try to remember, but just let me know so that I make sure to mark it and so that I know you're section 3.
okay, cool. I just didn't want to like get it confused.
Right.
Okay, thank you.
Okay.
How do we calculate what we need to get on the final again?
Okay, so to calculate what you need on the final, in Blackboard, find the total points, not your percent score, but it'll say you have, say if it says you have 750 points for the semester. Let's just pick a number. Then the cutoff for an A, you need 900 points. That's 90%. B is 800 points. C is 650 points. So you would subtract your points from whatever grade total point you want. Okay? So if I had 750 points, I need 900 for an A, so I would subtract that. I would have 150. I would need 150 points on the final out of 200.
Okay, thank you.
Okay? So yeah, just subtract and get the points, and that's out of 200 points on the final that you would need. Okay? Yes.
There's a question on the practice exam A, and it's about like the solubility.
Okay.
And it's like an AGCL one, and we were kind of confused on like the answer choices because it was like in terms of concentration.
Yeah, so it was,
Of
you
this-
put silver chloride into a
Yeah, it's that
solution
one.
of sodium chloride,
Oh, okay.
and it was saying that, this one.
Yeah.
It's saying
So
that,
go
I
ahead.
think it would be D, is the answer, but we were confused on why
Okay.
silver decreases.
All right. So this is a common ion one. So you have silver chloride, which is not particularly soluble. Okay, but a little bit of it will dissolve, but not too much, right? But now we're going to add a common ion. So sodium chloride is going to add chloride. Okay? So adding that chloride is going to shift the reaction which way? It's going to shift left.
So it's going to decrease the products.
It's going to decrease the products, but Le Chatelier's principle says it can only partially offset the change. So we add chloride, it doesn't remove all of it, only partially offsets the change. So if it shifts this way, silver is certainly going to decrease. Some of the chloride is going to go away, but not all of what we add. So overall, the chloride is still going to go up.
Okay.
So the correct answer is D. So, the first thing, a common ion for a reaction, for a solubility, is going to decrease the solubility. That's probably more important to know, but it decreases solubility by shifting left. Okay? In this case, it will decrease that ion. This ion, it doesn't remove all of it.
Okay, so
Okay.
then there was another question. It wanted like the PNH2.
Oh, yeah.
And I was like, what is that?
Don't worry about that. But it's just like how we got pH for water. So the parallel, and this is an old exam question from years ago, and students hated it. So I gave up on doing this. But this is just like, the autoionization of water. So you probably don't remember where we started the pH chapter, but we started going, well, you don't have to worry about H2O liquid because it doesn't enter into the equilibrium expression. But these would be 0 at the start. And then not much of water ionizes, but a little bit does. So we'd go minus X, plus X, and plus X. And at equilibrium, these would both be X, right? And so then we went Kw, which is 1 times 10 to the negative 14th, is equal to X times X. It's X squared. Anybody remember this?
Square root.
Take the square root. X is 1 times 10 to the negative 7th molar, which is not only hydronium, it's also hydroxide. So if you take the negative log of that, you get what? 7. So pH would equal to 7, and also POH would equal to 7.
Okay, so then you would just square root the K value
So-
and take the negative log.
So this one is
Value is not negative 14.
no, this is a different liquid, right? But liquid ammonia also ionizes even to a smaller extent than water does. But you could do the same ice table where you'd end up with X and X is equal to that. And then you could solve for X, and that P just means take the negative log. So pH, POH, pKa, pKb, it means take the negative log. Okay? So you won't see PNH2 on the final, but you should understand this. This is where the pH scale comes from, and it's from the autoionization of water. And we do get a little hydronium and hydroxide, and that's where we get a pH of 7.
We thought it was a typo.
It's not a typo.
Okay.
Yeah, that question, I had it on a normal exam years ago, and my students were just like, they didn't like it. They didn't like it at all. But I thought it was kind of, just for a practice final, get you to think a little bit. But,
Thank you.
all right.
Where did your reactants go? Because once you
The-
consider weak acid, weak base, and once you also have you have the X squared, so that's products. And then
Well, the reactants are both liquids, so they don't go into the expression. Okay, liquids and solids do not go into the expression. All right.
Well, I was going to ask about that one too, but while I'm up here, when we're calculating our grade, I'm trying to figure it out with the dropped quiz and attendance, do we just add whatever points are missing from there?
Well, so I already have dropped out your 2 lowest pre-lecture quiz scores. So the pre-lecture quiz score that's on Blackboard is with the 2 quizzes dropped.
Gotcha.
And the participation score, although I do have to go back in for a few students and for excused absences and change the participation, which I haven't done yet.
You're good.
I updated it sometime after spring break, but there's still a few. So participation should be right for most students because I did drop the 2 lowest. So those should be correct. In section 2, Alex should be correct now. So the points should be pretty
Listed up
close.
there.
The only thing really that's missing from section 2 is office hour points and SI points.
I'm not too worried about it.
But that should give you a good idea. So take those points, subtract it from, if you're shooting for an A, it would be 900, B is 800, C is 650. Subtract and then see how many points you need on the final out of 200.
Deal. Thank you so much. Have a
Okay, you're welcome.
good one.
So this question on the first test regarding the indicator, you're looking. I remember you were talking about.
Yeah, I just talked about that tonight. So all you got to do is take pKa of that
And match it closest to whatever indicator.
Well, whatever the pH is at the equivalence point. So this is a strong acid, strong base.
Yeah.
So what's the pH at the equivalence point?
Strong acid, strong base. It's going to be whatever, how it, like whenever it goes to equilibrium, you're going to have like, it's going to go to completion. So whatever's remaining from that.
Well,
right?
So at the equivalence point, all you have is salt dissolved in water.
Mm-hmm.
So
that would be 0.
No.
I mean, that would be 7.
For a strong acid, strong base, your pH will be 7 at the equivalence point.
Okay.
So you want an indicator. This says which
Closest
change
to
is
7.
closest to the equivalence point. So you're trying to find the one closest to 7.
Okay.
Okay, so you just have to take the negative log of that.
The notes you were taking on the half-life equation, could you put that back up really quick?
The half-life equation.
The nuclear,
Yeah.
the decay one.
This one?
Okay, I see what you did here. For some reason, I thought that the second one was 1 over. I thought it was from the second order reactions. But
No, these are all first order. So all radioactive decay follows first order kinetics.
Yeah.
So these are just two forms of the same equation. They're just rearranged.
Yeah.
And I think this form is easier to use if it asks for the amount at a later time. So you could have a problem where it says, you have this much of carbon-14 or whatever.
Mm-hmm.
Here's its half-life. What's the concentration after
certain amount of
200 years or whatever?
Okay.
And then that you would solve for that. Now you might have
Solve K separately.
Yeah, so it's a good chance, very common, that you ought to take the half-life to get K first to plug in the equation.
Mm-hmm.
And then, if it says how much do you have left after 200 years, you'd plug in the time. You'd plug in the initial amount, and you'd solve for the amount at a later time.
Okay. I also emailed you about our lost clickers with the 3 days that we.
Yeah, there's some other students that switch clickers too. Okay.
But
Okay.
the dates are in your email. So one of them is the day that we took our exam, 26 April. I think.
Which you wouldn't have needed that day.
Yeah,
so
so
it'd
I
just be
put
2
that
days.
next to it. But
So I do need to adjust yours too. There's two other students that sit by each other and they swap clickers at some point,
oh no.
not realizing they actually just left
Yes.
class with the other person's clicker, and so they used the other person's clicker for like 4 days or something.
We were actually in the bio building, went into a classroom after hours. Neither of us have a class in. There was just 2 clickers sitting on the table, and they were both ours.
Yeah, it was weird because it was in my pencil pouch. So they took all my pencils and my calculator and highlighters and everything, but they left the.
Clicker.
Yeah, so I didn't know if it couldn't be reassigned to someone or something. Maybe that's why they left it. But yeah, they got
We had
all
our
my.
initials on it. Got lucky here.
Yeah, I don't know. I mean,
Okay, yeah, I know this one. That's 6 Okay.
yeah. And then this form of the equation, I think, is easier if you're asked to solve for time.
Mm-hmm.
And with radioactive decay, it would be, how old is something?
Right.
And you would solve for time. Awesome.
Thanks for posting all the. That's a lot of work.
Well, so which ones?
Well, just because we couldn't make it to one of your review
Oh,
sessions.
posting these?
Yeah.
Yeah.
Even, Sophia was like, you guys are so lucky
Yeah.
to have Dr. C, because not many professors do that. And just thank you for that.
Look at this one. We are up to almost 2 hours and 5 minutes since we started.
Yeah, that's crazy.
That is crazy.
I don't know how you still have your voice left through this